also wait until I see it show up on my screen as well. All right, well then we'll get started then. Welcome everyone to the session 511, Atmosphere Theoretical to Applied Science. This is the second part. I'm your chair, session chair, Kyle Ziolkowski. So first of all, I want to take a moment just to acknowledge the lands of the indigenous people across coast to coast that we're on today. We acknowledge the ancestral and unceded territory of all Inuit, Métis, and First Nation people that call this land home. So just so to get things kind of rolling here, first up we have Cynthia. She's gonna, if you want to go ahead and share your screen and introduce yourself, we'll kind of get this session going.
Okay, yeah, is that okay?
That looks good to me, thank you.
Okay, so hi everyone, thank you. I'm going to present some work that we've done to include new lightning parameterization in the Canadian Earth System model and investigations into its impact on the simulated wildfires globally. Okay. Yeah, so wildfires are a complex but important process to include in ESMs because they're sensitive to changes in climate, and in turn they have impacts on climate. Wildfires emit greenhouse gases and short-lived climate forcers, and they impact the weather and cloud formation. Fire plumes can travel great distances, depositing dark particulate matter onto ice and snow, and they cause changes to vegetation as well. As you can imagine, climate change impacts wildfires to a large degree by changing fire weather. So it's when it's warmer, drier, windier. As I will show in this presentation, climate change also impacts the lightning frequency.
Cynthia, sorry to interrupt. We're not, it doesn't seem like we're live.
Oh,
Yeah.
sure. So should I go back to the beginning?
Yeah, go back to the beginning. It's not showing up on my other screen here. I have it up open on the other screen. Let's see if I refresh the page, if anything pops up. Hey, Chris, are you there?
Yeah, it also doesn't look live when I look as
It's,
well.
yeah, I see it's in part 3. We're live in part 3, not part 2, which this should be part 2. So I'm Okay. Okay, so Cynthia, we'll have you continue on then since we're live there. So really sorry about this. Yeah, we'll
Okay.
just in interest of time, we'll kind of keep pushing on, I think.
Okay, so should I start where I had been?
I'd start just from the beginning again. Sorry.
Okay. Yeah, no, okay. Yeah, okay, so hello again, everyone. So I'm going to present some work that we've done to include a new lightning parameterization in the Canadian Earth System model, and our investigations into its impact on the simulated wildfires globally. So, okay, so wildfires are sorry, I've got too many monitors. Wildfires are a complex but important process to include in our system models because they're sensitive to the changes in climate, and in turn they have impacts on climate. So it's a two-way feedback.
Cynthia, we see your
Yeah.
script, your
Oh,
Word
sorry.
document. Yeah.
Yeah, sorry. I'm sharing that screen. Okay, yeah. There we go. Okay,
Hi.
so it's too many monitors. Yeah, so the deposit on okay, so they emit greenhouse gases and short-lived climate forces. They change the weather in clouds. They deposit particulate matter on ice and snow, changing albedo. And there are changes to vegetation. And then in turn, the climate change impacts wildfires to a large degree by changing the fire weather and the lightning ignition and the fuel availability. So these feedbacks will require process-based interactive modeling between the land surface and the atmosphere in order to answer the questions: how will fires change in the future climate, and how will those changing fires impact air quality and climate? So on the right is a figure that you may have already seen showing the CAN-ESM model components. And for this study, we've started with CAN-M 5.1. And we've added the lightning parameterization. Not sure if you can see my cursor if I point to figures, but yeah. So, and then we've turned on the fires from our land model, class CTEM, and we've added the capacity for the atmosphere to use those online fire emissions so that the whole system becomes interactive. And I haven't touched on this yet, but we've also added a new fire plume height scheme for the vertical distribution of fire emissions. So that will come in the later part of the talk. Okay, so first, how is climate change impacting lightning, and how will it change into the future? So lightning has been changing as shown in this observation-based figure in the upper right. Blue regions are where lightning has decreased in the last 20 years, and red areas where it's increased. Unfortunately, most satellite-based lightning observations are centered on the tropics, and they don't observe much higher latitudes than about 54 degrees. But most of the lightning occurs in the tropics when you're looking at the global picture anyway. So in order to simulate lightning interactively, we've taken a relatively new lightning parameterization from the Ettenbaum et al. 2021 study. And it is based on large-scale atmospheric variables, CAPE, convective available potential energy, LCL, which is lifting condensation level, and R, which is a column saturation fraction. So this parameterization for lightning, it's desirable for an Earth system model to use because it's just one equation that works over the entire globe. And most other lightning parameterizations either don't work as well over the ocean as they do over land, or they're dependent on having accurate simulated cloud microphysics in the model, or they would need the model to be very high resolution, or they're reliant on highly uncertain simulated variables like cloud ice and so on. Whereas this lightning parameterization avoids all that, and it still gets very good results when we evaluate it against present day lightning observations. Particularly this lightning parameterization gets particularly good land-ocean contrast, which other models often don't get. And since we want to be able to do future projections, we compare our lightning results in CanESM to those from other studies that have done future projections of lightning. And those results are shown on the lower right. These are future minus present lightning from our study and 2 other studies. And again, the red is increasing and blue is decreasing. The one in the middle uses an upward cloud ice flux lightning scheme. This one by Finney et al. 2018. And that's a lightning parameterization that's closely based on actual physical processes of lightning creation. And so while those are kind of uncertain in models, its response to a changing climate should be roughly accurate or realistic. And then on the right is a study that uses the same lightning parameterization as we do, but applied in a different climate model, the CAM5 model. So all 3 have the decreasing lightning at tropical latitudes in a similar pattern that's already been observed, but continuing out into the future. And there are some small differences though. For example, in the middle of Africa, ours looks more like the ice flux trend decreasing, whereas that area is increasing in CAM5. On the other hand, in Australia, ours was showing an increase, whereas the other 2 show a decrease there, and so on. At mid to high latitudes, so like important for Canada, there's less lightning to begin with relative to the tropics, but it's increasing there in all 3 studies, though ours is like a less homogeneous results and is increasing to a lesser extent. So, next slide. So how will the future changes to lightning impact the burned area? Well, other than having an ignition source, the burned area can be highly dependent on temperature and fuel moisture as well, both in real life and in our simulations of fire. So the lightning could strike, but if it's been raining a lot leading up to that and the vegetation is very moist, then we won't get fire, or at least it won't spread as much before it goes out. And so that said, when we ran our simulations with both the evolving interactive lightning and a scenario where the lightning does not change, so keeping it constant at present day values, we actually see a very large difference in the future minus present burned area change, which is shown here. So the increase to the burned area in the tropics is very prominent in the case on the right, where lightning hasn't responded to changing climate, whereas the trend in burned area on the left is much smaller. And at high latitudes, like in the Siberian boreal forest, for example, we've seen increase to the burned area on the left when lightning is evolving and increasing there, compared to on the a little to no trend on the right when lightning stays the same. So the key message is that interactive processes matter, and we can't provide accurate projections of wildfires without them. So these next results I'm showing is a work in progress where we are adding another interactive process, which is that for the fire plume height. That's the vertical distribution of the fire emissions. And that depends on how big the fire is, because it's the fire's energy which lifts the smoke plume thermodynamically. So what CanESM had been using for vertical distribution of fire emissions was just an observation-based climatological plume heights in this lower right figure from its AERCOM study. And those were unchanging climatological plume heights, which means that we didn't have the vertical distribution of fire emissions responsive to possibly larger, more intense wildfires in the future. So why does that matter? Well, the long-range transport that we simulate is greatly impacted by the vertical distribution of the initial fire emissions. And if they're simulated too low in altitude, for example, then the emissions won't spread out as far. And our ability to simulate pollutant concentrations and deposition downwind is hampered. Also, the vertical distribution of some short-lived climate forcers will impact their direct and indirect radiative properties, So which we obviously want to be able to simulate well accurately in the climate model. So we chose the CFEPS thermodynamics based fire plume height scheme, which was developed at NRCan and it's used in ECCC's air quality model, GEM-MAG. And the figure in the lower left is the maximum fire plume heights from our first simulations using this plume height scheme in CAN-ESM, in sort of interactive with our CAN-ESM's our land models fire simulations. And we're comparing that against the sort of climatologically observed plume heights on the right. So this is only a couple of years simulation. So if a fire wasn't simulated in a grid cell in those 2 years, then it won't show up in this plot on the lower left. So we'll need to do much longer, like 20-year simulations to properly assess wildfire results because they're so interannually variable. So we'll be doing that in the near future. But for now, also to assess the new fire plume height results, we started to look at how black carbon, also called soot, is spatially distributed in CAN-ESM with this new scheme. So, these are vertical profiles of black carbon averaged over different latitude bands, like the tropics and the northern mid-latitudes and the Arctic. And the solid line is when we use our default model setup of the unchanging plume heights. And then the dashed line is a result using the CFEPS interactive plume height scheme. And on the right is the first minus the second, just to better highlight the differences. And it looks like because we have higher plume heights in the tropical areas, it's causing more black carbon to be lifted and transported out of that region, causing increases in the vertical profiles at the northern mid-latitudes and Arctic with these early results. So we're still tweaking this setup, and once we are happy with the evaluation, we'll go on to do future projections to see how fire plume height will change in warming climate. And so yeah, these are the take-home messages that I hope you'll absorb from this talk. So the new lightning parameterization based on the large-scale atmospheric variables is now in CAN-ESM, and it evaluates well for the historical period and projects lightning changes that are consistent with other more sophisticated, like let's say ice flux schemes. The impact of the evolving lightning on projected burned area is significant. On the right, we've highlighted the future change in burned area that comes from the 2 different SSP scenarios. And the different colored bars are showing the darker bars are when lightning was kept constant versus the evolving lightning in the lighter colored bars. So they're quite different from one another. And then the CFEPS plume height parameterization based on buoyancy was installed in CAN-ESM as well, and it allows fire plume height to evolve with the projected changes to fire size. And then future projections will be done, and as well as assessing the impacts on radiative forcing and long-range transport. And then just to end off, just some upcoming applications of this work. Basically, wildfires are a very hot topic. They're a very prominent extreme event that's getting worse in climate change already. And the impacts are really wide ranging from air quality, climate, health, socioeconomics, et cetera. And they continue to be very highly uncertain and active areas of research. So as such, we are hoping to participate with CAN-ESM with these model improvements for fire in these international projects. So the first mentioned here is the HTAP Fires project. It's a multi-model, multi-pollutant study that we're planning modeling experiments with over dozens of wide-ranging model types. And the experiments will include, baseline simulations, emissions perturbation experiments where we can quantify source-receptor relationships with fires and then the resulting air pollution. And we're planning also to do future simulations in this framework, both with prescribed future fire emissions versus comparing with models like ours that can simulate fires interactively. And then possibly benefiting from those HTAP model experiments is the Arctic Monitoring Assessment Short-Lived Climate Forces project, which is, we did an assessment report with them, and it was noted then that wildfires remain a large source of pollution to the Arctic because it travels long range. And then there's another activity under the International Global Atmospheric Chemistry, or IGAC project called BURNed, where we are planning a workshop this September on fire uncertainties in chemistry emissions and modeling. And then we're probably going to launch a special issue in a interjournal special issue. And then of course, in the climate community, there's the upcoming CMIP 7, where the AirChem MIP is being planned, probably also including simulations with interactive wildfires turned on this time around. Okay, that's it for now. Thanks for listening.
Thank you very much, Cynthia. Yeah, just in the interest of time, we're just going to have to move on to the next talk. If you have any questions for Cynthia, please put them in the chat, and I'll let you directly answer them in there, or we can, if we have time at the end. Sorry about the technical hiccup in the back end. And yes, welcome everyone to the theoretical atmospheric session, part 2. Sorry about the initial mix-up there. We had a hiccup on the back end. So next up in our session is Gabor. So Gabor, if you want to share your screen and introduce yourself, and we can keep this rolling.
Okay, can everyone see my screen? Or can you see it, Kyle?
Yeah, we can see it. Do you want to put it into presentation mode, I guess? Yeah, there you go. Perfect.
There we go. Okay. So my presentation today is lightning trends in Canada from 2002 to 2023. And this is taking lightning data based on the Canadian Lightning Detection Network, which is operated by Environment and Climate Change Canada. I also want to acknowledge my co-authors in this presentation. Bill Burrows is a research scientist in Edmonton, and Bob Koch-Tabida is also retired from Environment and Climate Change Canada, a research scientist in Edmonton as well. And I am located in Kelowna, British Columbia. Okay, so just a quick overview of the Canadian Lightning Detection Network. The network was established in 1988 and uses Vizsla lightning sensors. It covers Canada from the tree line south. So we catch pretty much all of the Yukon and then the southern parts of the Northwest Territories and Nunavut. And the network consists of 84 sensors. The data that I'm using in this presentation is cloud-to-ground strokes from 2002 to 2023. Just a bit of history, because we know as lightning sensors have evolved, they have gotten better at detecting lightning. So for cloud-to-ground strokes, the detection efficiency, or DE, has increased from 90% to 95%, since the establishment of the network. This is a fairly constant rate of detection efficiency. And because of that, it works better, I think, for trend analysis. In contrast, the detection efficiency for in-cloud lightning has increased from around 10% to around 50% now, so a 5-fold increase. A little bit more about cloud-to-ground strokes. So a lightning flash can produce multiple cloud-to-ground strokes and in-cloud pulses. You can see in this diagram there's at least 2 or 3 strokes showing in the photo that are contacting the ground. So it's these cloud-to-ground strokes that we're analyzing. So the national trend in Canada, taking the CLDN as a whole from 2002 to 2023, is a downward trend, a fairly steady downward trend, from an average of about 4.5 million strokes in 2002 to down around 3.5 million in 2023, the last year that we have data for. In fact, last year was the 3rd lowest national total of cloud-to-ground strokes. However, within the national data, there are some interesting regional differences. If we look at Western Canada, we see that we're seeing increased lightning trends, increased trends in cloud-to-ground strokes in Alberta, which is in the yellow color here, and blue in British Columbia as well. Sort of similar slopes, I would say, maybe a little bit less in BC than in Alberta. In contrast, in the eastern part of the prairie, so Saskatchewan, which is in green, and Manitoba in red, we're seeing a decrease in lightning cloud-to-ground strokes during this 22-year period. The decrease is most pronounced in central Canada, and in particular Ontario. This is traditionally the part of the country that sees the most lightning. So we can see quite a sharp drop off in Ontario shown in the blue, and Quebec, maybe a little bit less so, but still a steady drop off in the lightning totals over the period, from 2002 to 2023. Moving on to Atlantic Canada, obviously much less overall number of lightning strokes in Atlantic Canada, but still seeing this idea of decreasing trends, maybe a little bit flatter. The rate of decrease isn't as great as what we're seeing in central Canada, but still this idea of decreased lightning. Where things change are in the 3 northern territories. None of it is still flat, simply because we don't see a lot of lightning that far north. However, if you look at the Yukon in blue and the Northwest Territories in yellow, we're seeing a marked increased trend in lightning activity. So one of the things we thought about, given that we're seeing increases in the detection of cloud-to-ground strokes across the territories, with a general contrasted against a general decrease in Canada as a whole, I thought since I had data for some more regional data for BC, to take a look at what is happening in British Columbia. So if we break this down by BC Wildfire Service fire centers, taking the northernmost fire centers and the coastal fire center, we see increasing trends in lightning in all 4 of those fire centers. With the Prince George Fire Center, which comprises much of northern northeastern BC, seeing the greatest overall amount of lightning. So in the northern parts of BC, we're seeing an increasing trend in the lightning. But when we look at the southern 2 fire centers, so these are the southern interior, which includes Kamloops and Kelowna, where I live, and the Columbia Kootenays, we're actually seeing a decrease in the lightning trend. So that kind of fits with what we're seeing in Canada as a whole, with that sharp decrease across, in particular in central Canada, in in Ontario and Quebec. This suggests, so in BC, when we looked at the numbers, there is Bill Burrows and Bob Koshtabaya are doing further work. It's around 52 degrees north latitude where we see that the slope of the trend shift from a positive trend north of 52 north and negative trend south of 52 north. So really quite interesting. We're going to apply this work to the other provinces just to see where that trend line of shifting from a decreasing trend to an increasing trend happens. If we look at a seasonal analysis of lightning in the summer months, this is, apologies for cramming so much information into the graphs here. But we've got the north in yellow, or pardon me, the north in blue, BC in yellow, and Atlantic Canada in gray. We see a slight increase in the trends in, I'm missing the top of my slide here. I believe this is going to be winter. So a slight increase in the lightning in the winter, fairly steady state in spring. Summers, BC was already identified as a province where we're seeing some increase in the summer. The north seeing that increase in the summer. More of a marked drop in Atlantic Canada in the summer, whereas in the winter in Atlantic Canada we're seeing an increase in counts. And bear in mind that the amounts on the y-axis change markedly with the seasons, so you just kind of have to take that into account when you see it. Moving on to the rest of the country for the prairies and central Canada, so the prairies being Alberta, Manitoba, Saskatchewan, and central being Quebec and Ontario. We see a pretty flat trend, maybe a slight increase in winter in central Canada. Really no lightning to speak of in winter across the prairies, and that hasn't changed. Moving into the spring, we see a decreasing trend across central Canada, a slight increase across the prairies. Summer, when we see most of our lightning, decreasing trends in both areas, in both the prairies in blue and central Canada in orange. In the prairies, as we showed earlier, that we are actually seeing an increase in Alberta, but decreases in Saskatchewan and Manitoba. So, there's sort of more detail in these figures, but the one stat that really stands out is just a decreasing trend in summer across central Canada, and in the fall in both regions, seeing a decrease in lightning in both of those areas, in both the prairies and central Canada. So I've summarized these trends here in a table. North, there's no lightning in the winter, a slight increase in the spring, increase in the summer, increase in the fall. In BC, we're seeing a slight increase in lightning in the winter. In BC, most of the winter lightning occurs actually in the coastal areas. A slight increase in the spring, and then an increase in the summer with a decrease in the fall. Atlantic Canada, an increase in winter.
Net warning.
Okay, thank you. The increase is mainly in the offshore areas, in that area associated with the Gulf Stream. No increase in the spring. Again, that decrease in the summer, but a slight increase in the fall. Prairies, no lightning to speak of in the winter, a slight increase in the spring, but decreases in summer and fall. And for Ontario and Quebec, a slight increase during the winter, but then decreasing trends through the rest of the year. So, summary of our findings is lightning has shown a steady decline nationally between 2002 and 2023. The decline is most pronounced in central Canada, in Ontario and Quebec. Also seeing declines over the eastern prairies, Manitoba and Saskatchewan, and Atlantic Canada. An increasing trend has been observed in the 3 northern territories, as well as in BC and Alberta. But it's worth noting that while BC has seen an overall increasing trend, the 2 southernmost regions in the interior of BC have actually been showing a decrease. So for future work, work is underway now to examine data in all of the provinces, in particular the provinces showing an overall decrease in lightning, to see if there's an increase at some point over the northern areas of those provinces that is being obscured by the overall provincial numbers. We're also looking at a number of studies have reported increased positive lightning activity from thunderstorms in smoke-filled environments. So we're going through the data to see, we know that wildfire activity over Canada has been increasing. So we're going through the data to examine any regional changes or trends in the polarity of cloud-to-ground lightning strokes. So that concludes the presentation. Any questions?
Thanks, Gabor. Yeah, that's interesting stuff. Yeah, maybe we have time for like 1 or 2 questions. I see a question in the chat that there's actually 2 questions, but really they're kind of asking really the similar things. What causes the annual decrease in lightning in Canada? And there's a second question that asks something similar. Decreases in lightning in Ontario and Quebec in the 20 years are spectacular. What's the hypothesis? So what's the overall hypothesis on what you believe is causing this decreasing trend?
Okay, no, that's a good question. And yeah, the trend jumped out at me. That's why I wanted to dig into it a little bit more. Bill Burrows and Bob Koch-Tobias, so the co-authors in my paper, in 2018, they looked at this, and they also looked at CAPE values in central Canada, so convective available potential energy, and found that CAPE values during that same period had decreased over central Canada. So our hypothesis is that with the changes that we're seeing in climate, with the warming that we're seeing, the actual baroclinic zone is being pushed further north. So we're seeing less changes in the weather in the southern part of the country, especially in the summertime. So more persistent ridging, that sort of thing. And as that baroclinic zone is being pushed further north, we're starting to see increases in the lightning trends in the north. And that's really what we want to now look at, all the provinces and see if we can see where that inflection takes place. So in BC, we've shown it's around 52 degrees north. What's it doing in the other provinces? That's what we want to get at.
Sounds good. Yeah, one of the questions that I have about this analysis too is if you're bounding it by provincial borders too, it might be something might not be appropriate, just because we have lightning hotspots in Canada. Like for example, there's a hotspot in southeastern Saskatchewan, southwestern Manitoba, right?
Yeah.
That if you bound it by borders, then you kind of lose what that trend in that hotspot is. So I wonder if like looking at the identifying hotspots and then looking at the individual trends of those hotspots might be something that could be interesting.
Yeah, I know. I think that would be very valuable. Yeah, we know there's lightning hotspots to the lee of the Rockies. That's what you mentioned there in southern Saskatchewan, Manitoba, southern Ontario as well. I think that would be worth looking at as well. The data that I had accessible to me easily were based on the provincial boundaries. So that's what we used. I think the whole idea of this talk was just to present the information, just show what we're actually observing, and hope that spurs other people to start thinking about, some of the causes behind it.
Yeah, it's really interesting stuff. Thank you very much, Gabor. There's one other question in there, but I'll have to leave it till the end if we have time. I'll pass the ball over to you, Yucheng. It's your turn. If you want to go ahead and share your screen, introduce yourself. And,
it's okay.
Yeah, it looks good to me. Thank you.
Oh, thank you. Hello, everyone. I'm Yucheng Zi. As a visiting PhD student from University of Science and Technology of China, and studied at Dalhousie University and BIO with Jinyu Will Perry. Today, I will talk about the internal dynamics surrounding stratospheric warming events. As we all know, Earth's atmosphere includes the troposphere, stratosphere, mesosphere, and the thermosphere. So many people study at troposphere, but few people study at the stratosphere. What is stratosphere? Which is in altitude of 15 to 50 kilometers and reach in ozone, and the temperature increase with altitude in this layer. There is an important feature in the stratosphere, stratospheric polar vortex, so shown as SPV, which is a band strong westerly and surrounding the North Pole in winter. Next, this is a blocking high phenomenon in the troposphere, which is a dynamic phenomenon where force upward planetary wave. In the winter, due to the influence of planetary wave, there is a sudden stratospheric warming events occur in the winter stratosphere. Time scale are 10 to 30 days, and occurred by the SPV breakdown, and lead to the polar jet streams shift south, and cold air outbreaks and more extreme cold events. So SSW is an important precursor to prediction of extreme cold events. Next major objective during the sudden warming occurred by the deceleration of SPV. This panel is a time series of intensity of SPV. We gave the two cases, 27 year and 2021. We can see that in the 27 year is a significant dropout wind speed of SPV during the 10 days, but in the 2021 year, and gradually decrease of wind speed of SPV during the 40 days. We call this slow warming. Okay, we called it 27 year is fast warming events. So a question, if faster and slow warming events means more extreme cold events or less extreme cold events. So it's important to understand the internal dynamics difference between the fast and slow warming events. It's used for forecaster the extreme cold events. Next, classification of fast and slow warming events. And firstly, total 48 SSW events were selected from 1940 to 2021 year. And secondly, deceleration rate defines the deceleration rate of SPV. Look at this panel, which is the time series of intensity of SPV. Deceleration rate of SPV equal to the U maximum minus U minimum, and divided into the time difference. Finally, according to the normalized series of and 14 faster events were selected with R is more than 0.2 standard deviation, and 22 slow warming events were selected with R is less than the minor 0.2 standard deviation, and the rest of events is normal events. All data from EIA5 daily analysis and method include the composite analysis and use the epiflux to diagnose the planetary wave propagation, and use the Fourier analysis to decompose to the planetary wave. And next results, well, we gave the temperature and wind anomaly for the fast and slow warming events. Left panel is the composite zone warming temperature, and the right panel is a composite of zone zonal window. Blue line is the fast warming. Yellow line is the slow warming event. We can see the more in the faster slow warming event, more rapid warming and rapid deceleration of SPV from the 11 days, and the average deceleration rate is 3.77 meter per second per day. In the slow warming events, however, more slow warming and slow deceleration rate from the 34 days, and the average deceleration rate is 1.4. It's less than the fast warming event. Next, we're going to analyze the role of planetary wave and the fast and slow warming event. We gave the composite of geopotential high anomaly shading and climatology control at 500 millibar from the 20 days to 0 days before SSW. Our panel is a fast warming. First panel is slow warming event, and the total wave and wave 1 and wave 2. We can see that in the fast warming event, in the wave 1, positive and negative anomaly overlap the positive and negative climatology in wave 1. So, but in the wave 1, it's opposite to the wave 2. So, wave 2 is dominant in the fast warming event, but in the slow warming event it's opposite to the fast warming event. It's just dominated by the wave 1 in the slow warming event. Wave 2 is too weak. As we all know, blocking high is the main causes for the planetary wave. So we gave the frequency and the intensity of blocking high between the slow warming events. Up panel is frequency and bottom panel intensity. We can see that in the first warming event, blocking high over the Ural Mountain and Alaska and western coastline of Europe, and will enhance wave 2 in the first warming event. But in the slow warming event, blocking high just over the North Atlantic will enhance the wave 1 in the slow warming event. So it's so different in the two types of events. Next, we are going to use an epiflux diagnose the planetary wave. We gave the composite of epiflux and vector and divergence and shading from the leader 40 days to 0 days before SSW. Interval is 20 days. And our panel is fast warming event. We can see the fast warming event. Total wave dominated by the wave 2 and wave 1, but wave 1 is weak. And in the fast and slow warming event, intensity of total wave is weaker the fast warming event, and just dominated by the wave 1, and wave 2 make opposite effect. As we all know, effect of planetary wave can decompose to the linear and non-linear term. We can see the panel. Blocker line is a kilometer wave, and the blue line is anomaly wave. Linear term is interaction between kilometer wave and anomaly wave effect. Non-linear term is just anomaly wave package effect. So next, we give the result. Our panel is fast warming event. Bottom panel is a slow warming event. We can see the total wave in the fast warming event, dominated by the non-linear and linear term. But non-linear term is more than linear term, and just dominated by the wave 1 and wave 2. But the linear term just dominated by the wave 2. And in the fast in the slow warming event, total wave is just dominated by the linear term and wave 1. So non-linear wave will lead to the fast warming event. Next conclusion is total 48 SSW events will divided into the fast and slow warming event. And planetary wave in the fast warming event will dominated by the wave 2, where wave 1 is dominant in the slow warming event, and blocking high in the Ural Mountain and Alaska Mountain enhance wave 2 in the fast warming event. And non-linear dynamics play an important role in the fast only event. That's all. Thank you.
Excellent. Thank you. Is there any questions? I don't see any in the Q&A. I'll double check the chat in case someone put something in there. There's a bit of a delay when someone asks a question.
Okay.
And I just want to mention to the audience too, if you have a question, don't try to enter it in, when you think of it, or not towards the end of the presentation, or try to be quick about it, because there's a bit of a delay trying to get sometimes the questions in. So try to get your question in as quick as you can so that we can see it. I don't see anything right now, but that's very interesting work. I mean, it's something I've always been pretty fascinated about. So it's I found it really interesting.
Okay, that's okay. A few people study it. So I know.
Yeah, thank you.
Thank you. Okay.
Yeah, we'll move on to the next presentation, which is Dr. Fabry. If you want to share your screen and introduce yourself, we'll keep on moving.
So now for something completely different and very applied in nature. This presentation is a follow-up of a previous work presented 2 years ago on and it dealt with how energy demand and renewable supply may or may not complement each other. Now, since I don't expect anybody to be here to remember what was said 2 years ago, I'm going to start with a kind of recall. So when we look at the possibility of powering our future with renewable energy, we're concerned about the episodic nature of renewable energy. Renewable energy, sun and wind in particular, are very episodic. There are regions in the atmosphere where we've got more winds and regions where there's less winds, and similarly for sun. The interesting thing is that demand is also modulating with time. There are regions where atmospherically we expect warmer temperatures, and there are other regions where we expect colder temperatures. And in winter, where you have cold temperatures, well, guess what? Demand is going to be higher. And similarly, if you have warmer temperature in summer, you expect demand to be higher. So supply varies with time and demand varies with time. And the traditional conclusion is that, well, supply and demand are messy and uncorrelated, and we have to live with that. But the fact is, if you look at this conceptual picture here, we can see that both heating and the demand part, whether it's heating or cooling, and the supply are actually shaped by similar patterns, which are basically the weather systems. There are regions where we can find winds, there are regions where we can find sun, and there are clear regions where we can find sunny and or cold and warmer weather. So for example, if you look, if you're in winter and it's very cold, typically you are on the left side of the picture. And well, it's typically sunny because there's typically a high pressure there, but there's typically no winds. Similarly in summer, if you are very warm, you're on the lower right side of the picture typically, and it's warm and it's generally sunnier. And but it's typically not windy. So what you find is that solar energy tends to be naturally correlated with needs, which is great. But when you think of wind power in particular, it's messy. So if we look, for example, in winter, where's the wind? Well, it's not nearby, it's east, because basically the system that was basically the system that is bringing the cold air is now east of you. So if you look on the right side, the correlation between how much power is needed in New York City, I could have done that with Toronto, Montreal, this result would be pretty similar. And where there's supply of wind, this is in winter, so we have negative correlation, basically in New York City, as well as in most cities. When it's cold, typically we have lower winds. And if we want to find winds, where we're going to find them? East, and also in the mountains, and I'm not exactly sure why the mountains. So this was the conclusion of the first work. But when we start to think about it, we realize that we may have done an injustice. Et essentiellement, pour pouvoir comprendre ce qui se passe, imaginons que nous habitons ici dans une région froide et que la dépression se retrouve plus à l'est. C'est vrai, le vent est loin à l'est, mais ce qu'il faut se rappeler, c'est que 36 heures plus tôt, peut-être, la tempête était là où on habitait. Et donc, il est possible qu'au lieu d'aller chercher l'énergie très loin dans l'est, il serait possible d'aller la chercher simplement, la stocker pendant 1 ou 2 journées avant d'en avoir besoin. Donc, nous nous sommes demandé, est-ce qu'on peut refaire l'analyse en tenant compte du fait, non seulement en regardant l'énergie disponible le jour même, mais l'énergie disponible 1, 2 ou 3 jours auparavant. L'analyse a été faite en utilisant les données de RA5 pendant une période de soixantaine d'années. Et nous avons pris les températures pour pouvoir calculer la demande. Nous avons pris l'illumination solaire et le vent en altitude pour calculer l'offre. Et nous avons calculé les corrélations basées sur cela. I'm going to present the initial results for New York City, recognizing that, again, this is representative of most of the east of the country. So what we're going to focus first on the upper plot here that looks at the correlation between demand and wind on the given day. And this is the same plot I showed before, negative correlation nearby, positive correlation far in the east and in the mountainous areas. But if I look at the plot of the correlation with the wind of the day before, well, the storm has moved backwards in some way, and there's a lot more wind. So now suddenly New York City has more winds and the same, again, it's the same is true in other places. And 2 days before, we have a kind of a similar picture. So if I look here in the on the right, the plot on the right side, what we looked at is the demand and supply around cold days in New York City. So we looked at the top 20% cold days, and we call it day D, and we looked at how much the demand is higher than average. So the demand is 1.4 times the average. Now it's colder, so we need more energy. And it, of course, decreases before and after. And then we can look at supply, and we look at supply from New York City. So again, at New York City on the day, it's actually about average, the supply. But if we look at a day before, we actually have 20% more wind. The other place that I looked at is looking at Maine, where we have positive correlation. And we have positive correlation and higher production, not only on the day of, but also the day before. So there's some potential of stocking up on wind energy just before a cold day arrives, if we can rely on that. Now, I focused on the line. What's important to realize is that there's an enormous distribution. These bar graphs show the anywhere from the 25% probability to 75% probability. Basically, there's a lot of days where the winds is still going to be weak, and there's some days where we're going to have plenty of wind available to produce our power. We can repeat the same exercise. We can do it for solar energy. I thought solar energy is positively correlated, and there are many places where it's sunny when it's cold in New York City. But the same is true the day before. There's also typically more sun, and when you go 2 days a bit below, it gets more neutral. If we look on the last column about how much energy is needed or can be produced by the sun in warm days, and again, a slight positive correlation on the day and the day before. Well, it's normal because on day where it's warm, typically it has been sunny not only on the day of it where it's warm, but a couple of days before. So there is some possibility to stock energy. For wind in summer, for New York City, and for most of our areas, it really doesn't help. Wind and in summer is really not well timed wherever we look at things. So this is for New York City. We can look at the results elsewhere, and I won't show a lot of plots, but basically for solar energy in the eastern 2/3 of the North American continent, as well as on the West Coast, the solar energy tends to track or precede weather demand. So we can have potential to stock that energy. correlation is generally negative on or prior days of high demand in the Rockies. In the Rocky area and downwind, there's typically it gets cloudy when it gets cold, and there's relatively little that we can do in winter, especially. For wind energy, it remains for the reasons that I described before. It's typically poorly timed, except on the West Coast and on the Adirondacks, where there's a bit of positive correlation between when it's needed and when it's available. But if you use the winds from 1 or 2 days before, it helps. However, in summer, there's nothing to be, no gains were obtained by looking at days before when it's particularly warm. There typically is no wind. And that concludes my talk. Thank you.
Thank you, Frédéric. Just looking to see if there's any questions that have come in, and nothing has come in thus far. It's just really interesting analysis, like looking at it from this point of view, and I think it's something super important. Have you presented it to like any energy companies or anything like that? Are they interested in this type of work? Is that what kind of?
I haven't been able to contact. It's not by lack of trying, but I haven't found the right door yet. I've presented it at other scientific conferences in meteorology, but not I haven't succeeded in knocking the door at power companies. But certainly, especially in the East, there's a lot of potential of if you look at, especially when we in Canada, where we have large provinces, so you can go east of Quebec and be able to benefit Western Quebec. In smaller states, the distances that are required are much, they're not much bigger, but they're cross state, so they become more complicated to transport energy because you change utilities. But yeah, I'm hoping people will see it.
Yeah, and you know, that changes even out here on the prairies, right?
Yes.
Those bands and just how weather interacts, like in a post-frontal situation where it, you know, you're starting to get a lot of cold air advection and cold air settling in, the winds can be howling across the prairies.
Well, so can it here. Typically on the first few hours of a cold front, it is howling, but if you think of your cold days in the prairies, I'm sure after the storm passes, the next day you've got a glorious sun and typically much less wind, and it's freezing.
Yep, that's right. Okay, that's excellent. We'll move on to I think Maxim, you're supposed to present. Yes, you're up next. And if you want to share your screen and introduce yourself, then.
Hello, everyone. I'm Maxim Couillard, and I'm excited to be sharing with you my master's research. If no one says otherwise, I assume you can see my screen and hear me. I will be sharing my master's project on investigating thunderstorms in mountainous regions. So to begin, we're investigating thunderstorms because our current knowledge of convection and thunderstorms is still incomplete in this field, and numerical models still continue to make errors, and we do not fully understand processes, especially with surface and land interactions. So just a quick thermodynamic review on how thunderstorms form. We have a little schematic of a tephogram with dew point and temperature. So when a parcel of air is forced to rise, it will cool adiabatically at a dry rate until being saturated, and then it will cool at a slower rate because it is undergoing moist processes. So when the parcel of air is warmer than the environment, we have this region of convective available potential energy, which gives storms more frequency and more intensity, stronger updrafts, what we look for positive storm factors, and convective inhibition is regions where a storm or a rising parcel can be negatively buoyant, inhibiting the reaching of this area in the green. This area here is the level of free convection, where parcels can rise buoyantly, and just saturation being reached is the LCL, lifted condensation level. So simple mountain processes everyone knows. Air is forced to rise and cools, and we get precipitation on mountains. With regards to convection, also well understood, we have differential heating, warmer mountains, colder air in surroundings, and this leads to circulations that create convection. So, despite all this, our research has found significant minimum of convective strength and occurrence on mountains, and we are investigating why. These are our two mountains of interest in the United States we will be looking at. So to begin, we looked at a host of independent observation, beginning with radar. So this is radar statistics of 40 dBz exceedance. So how frequently this level is surpassed. And we see minima on 2 locations in this Appalachian mountain range, but we take our radar data with a large grain of salt because we know there will be non-meteorological reasons for mountain storm holes due to beam blockage. As we've already mentioned a few times in this session, cloud-to-ground lightning data can be very useful, and we don't believe that the mountain height is creating any bias to this data. So this shows a fascinating 2 to 3 factor reduction in lightning frequency on the summit of this mountain range versus the sides. And lightning is indicative of updraft and convective strength that creates charge separation in clouds. Prior research also finding this was a 2020 paper looking at lightning frequency per thunderstorm day. So this minimum on the 2 mountains shows we are looking at frequency and intensity minima. So even on days where there's thunderstorms, they are weaker. And on the top right here, we did analyses of ERA5 reanalysis. And we see slightly different signal with the maxima of precipitation on the higher mountains to the south, but still a pretty pronounced minimum in the location of interest. Continue. Just a quick look at mountains closer to us in the Adirondacks. We also found a rather significant reduction of convective frequency. We chose to focus on Appalachian Mountains due to their simple linear structure and ease of simulation, as well as the higher frequency of storms in the southern US. So because this pretty low resolution for convection, ERA model is able to reproduce our desired signal, we looked at some larger scale processes that could result. Thermodynamics such as CAPE or blocking, but is a rather tricky problem choosing days where the mountain could be killing storms. So we came up with a couple subsets from top 10 percentile CAPE to top 10 percentile rainiest days in this domain average to look at when convection's actually happening. And that gave us 138 days. So the first clue from the ERA5 was this significant minima of convective available potential energy. So this is the average values, about a factor of 2 difference. And this is even on the convectively rainiest days, we still have this minimum of convective available potential energy. So this will significantly limit the potential of convective updrafts and maximum storm strength. But simply finding less CAPE doesn't necessarily mean less convection, because the mountains are able to very efficiently trigger convection as we had started off in our schematic, but it is an important part of understanding this minimum. Complicating things further, we also have a minimum of convective inhibition because these mountains are elevated and heated. So we can form convection easier. There's less barriers to its formation, but it is forming an environment with poorer CAPE, which is very interesting for our topic. CAPE is a combination of moisture, stability, and temperature. So kind of partitioning this, we know mountains will obviously be colder than lower elevations, but with respect to potential temperature, they're actually maxima of 2-meter potential temperature, but mountains end up being drier than the surrounding lower elevations. Going up just above the surface at 850, the story's a little different, and we actually have a moisture maximum in relative and absolute humidity. So we have our dry mountain surface, but just above it, saturated, cloudy environment, which makes understanding this CAPE minimum rather complicated. If the surface is a potential temperature maximum and just above the surface, we're also rather strong moisture maximum as well. Some larger scale hypotheses we looked at, there's plenty of literature on Lee cyclogenesis and frontal dynamics papers. This interesting one on the right was showing that a cold front can actually teleport to the other side of the mountain and form a new front while the original is actually dying on the upslopes, and the forcings can kind of be separated from either side and also upper and lower level. So while cold front passages are pretty rare in the summer and not directly leading to this minimum, we've seen very similar effects with mesoscale convective systems or organized convection. So an example radar here, lovely, well-organized storm approaching the dotted lines here representing the mountains. It ends up dissipating along the slopes, but before it reaches the other side, a new convective line forms and ultimately takes the energy and keeps going, leaving the mountain receiving a minimum of thunderstorm and this new one accelerating away. Some idealized simulation work into this was hypothesizing that as a cold pool outflow descends a mountain, it can accelerate too quickly and thin too much to actually allow efficient lifting for convection to form, making these Lee mountain slopes not able to produce convection during these organized times. So we ran some experiments investigating not the whole mountain itself, but rather storm scale terrain impacting gust fronts and storm organization. And to do this, we ran high resolution 1 kilometer scale WRF simulations, and we smoothed the terrain so we could run real storms, real cases with real terrain and smooth to directly compare the impacts of the mountain on the storm. So just a quick example of a cross-section from one of these case days. On the left is real topography. On the right is our smoothed. We're looking at colored contours of equivalent potential temperature. You can see the gust front and the cold pool behind. And these hatches popping up and down are of wind speed, vertical wind speed of greater than 1 meter per second. So that's indicative of convection.
2-minute warning.
Okay, and can see that actually smoothing didn't end up helping the organized storms as much as we thought it would, but it may play an important role in storms that form on the mountain inhibiting their organization. So my current work is trying to quantify these simulations and actually prove this MAT minimum. So we're segregating parameters from left, right, and on the mountain. This is for precipitation, but recently in the past week, we did elevated Graupel, integrated Graupel through the column, and that showed a significant minimum on the mountains that matched our lightning minimum, which we are very excited about. And lastly, our main hypothesis is that this is a timing argument, that in the diurnal cycle, because we have a minimum of convective inhibition, storms form easier on the mountains and earlier in the day, where there is less CAPE available, and ends up shutting off convection in the afternoon. So the cloudiness from the earlier storms ends up inhibiting stronger storms in the afternoon. So just my quick conclusion slide. We obviously do not understand everything there is to know about thunderstorms and mountains, as our preconceived notion is that they should be good places for thunderstorm activity, and we're finding significant minima on these rather small East Coast mountains. And we explored a series of dynamic and thermodynamic reasonings for this, with our main hypothesis being simply that the earlier and easier to form storms end up forming in a poor convective environment and stopping storms from forming later in the afternoon. And that is all I have. Thank you for your time.
Thank you. Are there any questions out there? I don't know if I don't see anything. Let me check the chat. Nothing in the chat so far. And same with the Q&A. I think we'll wait and see if anything comes in. Since we're a little bit behind, we'll just move on to the next presentation, which is Amber Ross. If you want to share your screen, and there we go. Perfect. We can see it. And if you want to just give yourself a quick introduction, and we can proceed. We can't hear you, Amber. If you're...
Alrighty. Can you see me now?
We can see and hear you now. Perfect. Thank you.
Okay. Perfect. So thank you. My name is Amber Ross, and I am with the Climate Research Division of Environment and Climate Change Canada. I'm going to talk about the low porosity double fence windshield configuration for improving solid precipitation measurement. And before I start, I would like to acknowledge that I'm doing this presentation on Treaty 6 territory, the homeland of the Métis, and the traditional territory of many nations, including the Cree and Dakota. So why the need for this study? Well, the in situ measurement of solid precipitation is one of the hardest meteorological and climatological parameters to measure. Solid precipitation measurements are subject to undercatch due to wind, and windshields are used to improve the catch efficiency of solid precipitation. Now, the WMO Solid Precipitation Intercomparison Experiment, or SPICE, introduced the double fence automated reference, the DFAR, and that's shown in the photo here. And it consists of an automated gauge inside of a large wooden double octagonal wind fence. Now, although the DFAR significantly reduces the wind-induced undercatch, it is expensive to install. It has a large footprint, it is subject to degradation, and it's difficult to maintain, especially in remote locations, making it unfeasible for use in operational networks. So that leads us to the low porosity double fence windshield. So from that top picture, you can see that this windshield consists of 8 panels used to form an outer octagonal shield. and 4 panels used for an inner square shield. So just a little bit of a background. This was developed and tested by the National Oceanic and Atmospheric Administration for use in the US Climate Reference Network. It has a substantially smaller footprint, so 4.9 meters wide compared to the WMO SPICE DFAR, which is 12 meters wide. It's constructed of off-the-shelf chain link fencing material that's virtually maintenance-free and relatively easy to install, making it deployable at almost any station. Intercomparisons of the LPDF at test sites in the United States showed very satisfactory performance for salt precipitation measurement. And for assessment in conditions more typical of the Canadian prairies in the Arctic, so in other words, high exposure with elevated wind speed during snowfall events, the LPDF was installed at our Bratz Lake, Saskatchewan super site this past fall. So here are just a couple of photos of the LPDF at Bratz Lake at different stages of assembly. The left is the structure without the vinyl slats, and the right is the completed installation. So I'm just going to go ahead and jump into the results. So here is the accumulated 1-minute time series for this past winter season for the double fence automated reference in blue, the low porosity double fence in orange, the double altar windshield in yellow, and that configuration is shown in that top photo, and the single altar windshield in purple, and that's shown in the bottom photo. So all the gauges, they were filtered using the supervised neutral aggregating filter, and this filter balances the positive and negative noise, and it accounts for diurnal oscillations, so it smooths the data, and it's also used to manually adjust the time series for evaporation. So as you can see here, the DFAR recorded the highest precipitation amount, with the LPDF coming in second, followed by the double altar and the single altar. So comparison of the DFAR, or comparison to the DFAR, shows a relative total catch of 81% for the LPDF, 75% for the double altar, and 72% for the single altar. So the 1-minute data was converted to daily events. And what you see here is the analysis based on these daily precipitation events. And we are using the DFAR as the reference precipitation. So first off, the top left shows a scatter plot with catch efficiency on the y-axis. And this is just defined as the LPDF precipitation divided by the DFAR precipitation. And we have the wind speed on the x-axis. Rain is shown in cyan, snow in blue, and mixed in magenta. So in general, what we're seeing from this plot is that the catch efficiency is going down as the wind speed increases. And this is something that we expected. Looking at the scatter plots to the right, so with the orange, we have the LPDF precipitation on the y-axis and the DFAR on the x-axis. And starting with rain, you can see that most of the events fall along that 1-to-1 reference line. So both gauges are catching similar amounts of precip. For snow and to a lesser extent mixed, there are several events where the DFAR reference is catching more than the LPDF. So looking at the statistics for the low porosity double fence down in that pink table, we have the total number of daily events for each precipitation phase. And now this is always an important consideration. This analysis is based on one winter season, so we only have 8 rain events and 16 mixed events, but a relatively good amount of snow events at 32, and that's our main focus, so that's good. Next, we have the probability of detection. So this is the percentage of events where both the gauge under test and the reference recorded precipitation. So we have 100% for those 8 rain events and 94% for snow and mixed, which is a very high number. And high probability of detection is important because you are simply unable to adjust the data for wind undercatch if the gauge didn't catch anything. Next, we have false alarm reporting, and this is the percentage of events where the gauge under test reports precipitation, but the reference does not. So we have 0% for rain and mixed, and only 3% for snow. So very good numbers here. And the last metric I'm going to touch on is the relative total catch of the LPDF when compared to the DFAR. So we have 95% for rain, 89% for mixed, and 70% for snow. So in comparison with the single alter and the double alter shown in these blue tables to the right, we can see that a 70% relative total catch for snow is a notable improvement from the single alter at 56% and the double alter at 58%. And just a small caveat here, we did have some data issues with the double alter gauge along with the small data set. So this number is typically a bit higher at around 65% for snow events at Bratz Lake, which is still lower than the LPDF. All right, next I'm going to go over some case studies, starting out with events where the catch efficiency equals 0. And these are circled on the catch efficiency plot there. So there is only 3 events where the catch efficiency equals 0. And for all these events, the LPDF did not record any precipitation, while the DFAR only recorded very small daily amounts. So 0.4, 0.1, and 0.2. Now, these could be light precipitation events, but they could also be due to blowing snow or artifacts from noise in the gauge signal along with the filter smoothing. It's not quite clear, but it's not too concerning. Next, here are some high wind speed snow events, which are again circled in the catch efficiency plot. So on January 11th, the LPDF recorded 0.4 millimeters of precipitation and the DFAR recorded 0.5 millimeters. On January 14th, we have 0.4 compared to 0.9. March 5th, 0.4 compared to 0.3, so a little bit higher for the LPDF. And April 19th, we have 0.7 millimeters compared to 2 millimeters for the DFAR. The wind speeds here are all in the range of 7.3 to 8 meters per second, so very high. So the takeaway here is that the LPDF is recording solid precipitation even at these high wind speeds. And in most cases, the LPDF precipitation is comparable to the DFAR. All right, so this is just a bit of an aside to illustrate the influence of gauge rim heating. So a gauge rim heater, it just simply heats the gauge inlet or the chimney, so any solid precipitation that sticks to it is melted quickly into the bucket contents. So the DFAR and the LPDF, they both have gauge rim heating, while the single alter and the double alter do not. So this is a freezing rain event, and just looking at these photos here for the single alter gauge, at 1400 UTC, we see that there's some ice accretion on the shield surfaces. At 1600 UTC, we see some snow sticking on the inside of the chimney. And at 1800 UTC, we see that that sticking snow has cleared. So sometime between 1600 and 1800, the snow sticking to the inside of the inlet fell into the bucket. And we see that little increase in the bucket weight in the time series. We suspect that this also occurred with the double alter with this little blip in the time series, but we unfortunately don't have photos of that gauge. So the key point here is that this issue just does not occur with the DFAR and the LPDF, both of which have rim heaters. Okay, so just a couple of considerations in terms of durability. After one winter season, there is no deterioration observed. The screws mounting the windshield to the ground just needed to be tightened slightly. In terms of snow accretion, like the alter shield, the LPDF is susceptible to snow sticking to the fence. Implications are unclear, but it may actually decrease wind flow around the gauge, which in turn could potentially improve the catch efficiency. And in terms of cost, it's about $4,500 for the double alter windshield and about $3,000 for the LPDF windshield. So in summary, the LPDF, it performed better than all other gauge configurations that we tested. A 94% probability of detection for snow and mixed precipitation is very high, which makes transfer function wind adjustments achievable. So again, this is critical because the gauge must catch something in order to apply an adjustment. And in other words, you can't adjust zero. And finally, this analysis was based on just one winter season, so more data is needed for a thorough assessment. Thank you very much. I am happy to take any questions if there is time.
Thanks, Amber. Yeah, we can definitely take time to answer some questions. And I see there were some questions in the chat for Maxime, and he responded. I don't know if you want to just expand upon that while we wait for any questions to come in for Amber. If you want to do that, Maxime, or if you're comfortable with what was asked with your answer.
Sure. It was just a simple question of if we've looked at West Coast mountains like the Rockies, which obviously is the first question you would think after seeing our signal. We've just we're exclusively looking at East Coast, being based in Montreal, and just seeing such pronounced storm minima signals that haven't really been explained anywhere else. And also on the East Coast, there's storms that can propagate from the west that either survive or don't, versus like the Rockies are so tall and dense that there's not really any storms coming from the west side for us to tell if they're killing storms or not. So that's kind of a basis for our decision.
Thanks. Amber, we do have one question for you. The question is, does wind direction affect results? Example, the fences from one instrument shielding the other test instruments.
So we aim to have enough space between all of our instrumentation in order to prevent this from happening. However, I mean, that is possible, but it's not something that we have looked at directly.
Sounds good. Thanks. Just, do we have another? Stuff flips around on me. Okay, I think this is a question for you again. Where is the wind speed being measured, and what gauge were you using? The same for all shields.
So I assume you mean precipitation gauge. So for the DFAR, the LPDF, and the single alter, we used a GNR gauge. And for the double alter, we used a pluvial gauge. However, in my opinion, it doesn't really make a difference because we are using the raw data coming out from each gauge. And one of the results from SPICE was that there really wasn't much of a difference between a GNR and a pluvial gauge. And the other question, and the wind speed is being measured at gauge height, so 2 meters.
2 meters.
2 meters.
I just want to go through this and make sure I don't miss anything here again. I don't see any new questions. There was a question that we couldn't answer earlier, just in the sake of time, but we kind of caught up here. So the question was, are there any plans to make CLDN data open? So the Canadian Lightning Detection Network data open. I don't know if Gabor, if you have any further comments on that, but there was an answer: plans to make the CLDN data open. The data is available for research purposes. We ask that users sign a data user agreement before making the data available.
Yeah, nothing more to add to it than that, Kyle. I routinely get requests from academic researchers asking to use the CLDN data, and it's not a problem. Just ask that they sign the agreement and that they provide us a copy with any of the research that results from the use of the data, and accredit Environment Canada as a source of the CLDN data.
Perfect, thank you. All right, I don't know if I don't think we're hope I'm not missing any other questions in here, but I would like to thank again all of the presenters for their work and the presentations. They're all very interesting, super great information. Found it quite a fascinating session. I apologize that we had some technical issues off the start that kind of threw a bit of a hiccup into the whole thing. But we caught up with time and stuff, so I'm happy that we were able to get caught up anyways. So the next session is part 3. It's the last part of this the atmosphere theoretical sciences, part 3. It'll be actually in this same room, I guess, virtual room, and that will be starting in about 15 minutes time. So we'll see you then.